Okay, good morning, everyone. I hope you had a good week and you learned a lot last week. If you have any questions about the material covered last week, please feel free to email me and I will try to incorporate it into the classroom. Somehow I will start the class answering your questions. Okay. So today I will pick up where Professor Beer left, and actually we're going to go to L'Hôpital's rule. Okay. So for tomorrow, what I would like you to do is do the homework I assigned about L'Hôpital's rule. And if you have any questions that about the material that was covered, anything you did not understand, I would very much like you to ask me tomorrow in class. So this will help me to figure out what you know and you don't. And also, as you know, you have an exam this Friday. Your review is on Brightspace. I hope you guys got started. All right. Any questions before I get back? Any questions? Okay, so we're going to talk about L'Hôpital's rule that I know Professor Beer started it, but we will go over it anyway. So let us recall what is the situation here. So something we've talked about at the beginning of the semester. Of course, we talked about that at the beginning of the semester, but now we're going to talk a lot more about it. So suppose you have two functions, and that's their behavior. Near a point A, the function f become close to 0, and g become close to 0. So both f and g becomes really, really very small. Then if we look at the ratio, f over g, so when x become close to z, this become close to 0, and this become close to 0. So the limit of f over g, we give it a name, and we call it an indeterminate form of type 0 over 0. And why did we call it an indeterminate form? Let us remember where this word indeterminate form. The idea is called indeterminate form because that's the scenario. When x become close to a, the numerator is very small and the denominator is very small. So the ratio, we actually don't know whether it's going to be small or large. That's really what's happening, why it's called indeterminate. So it's like if we think about numbers. If f become very small, like 10 to the minus 10, that's really small. And you divide it by something also small, like minus 5, this is way, way, way smaller. So this is going to drag the whole thing 10 to the minus 5, make it small, because this is way, way smaller than the denominator. If I flip those around, the denominator become way, way, way smaller than the numerator. So this will become 1 over 10 to the minus 5. It means 10 to the power 5. This is way, way smaller. It's going to drag the whole thing to infinity. So indeterminate because we really don't know what's going to happen. It depends how small the numerator and how small the denominator. That's why the word indeterminate comes from. And then there is another kind of indeterminate form. If the numerator becomes very large and the denominator goes to infinity, so that's really the second scenario. And then this is also called indeterminate of type infinity over infinity for the same reason. If the numerator grow very fast and the denominator grow very fast, the ratio we have, this is very fast and this is very fast. The idea, you can think of it as a battle between two functions. Which one is winning? Which one is going faster to infinity? If the numerator goes very much faster, the whole ratio will go to infinity. If the denominator goes way faster, the whole thing will go to 0. If they go at equal speed, let us say, for example, f is 2x cubed, and that's f. And g is, let us say, 5x cubed. Then both goes to infinity, but the ratio will go to 2/5 because they go to a kind of very similar speed. So this is also indeterminate of type infinity over infinity. It means we really don't know the limit by looking at it. We have to manipulate. So here comes L'Hôpital's rule. So at the beginning of the semester, as I said, we looked into those. We developed some tools. But L'Hopital's rule is a tool, another tool, you can think about it. L'Hopital's rule is a tool, a way that helps me to compute those particular type of limit. And that entails the following. Suppose f and g are two functions, such that when I take the limit of f over g, I have an indeterminate form, either of type 0 over 0 or infinity over infinity. And that's crucial. L'Hopital's rule applies only in those two scenarios, nowhere else. Then the limit of the ratio of f over g is the limit of the derivative of f over the derivative of g. Okay, so that's what L'Hopital's rule tells us. And we're going to start applying it using several examples. All right. So let's start with the first, some very basic example. Let's compute the limit.
I have a question real quick.
Of course.
So it's only 0 over 0 and infinity over infinity, not negative infinity over negative infinity?
Oh, yeah. Yes.
Okay.
Yeah, it's the same because intuitively it's the same, right? Because even if you have infinity over minus infinity, do you think it's the same idea? This becomes very large. This becomes very negatively large. So it's like if you have something like that. If you have 2x cubed, which is very large, divided by, let's see, minus x4. All right? This one will go to where? So let me write it in black. When x goes to infinity, the numerator goes to infinity. The denominator goes to minus infinity. But the ratio will go to where? Can you guys tell me quickly by looking at it? It's simple. When x goes to infinity, the ratio will go to where? 0, because this will become what? 2 over minus x. When it goes to infinity, this will go to 0. Okay? If I flip, so I take x4 over minus 2x cubed. This is also infinity over minus infinity. But intuitively, this goes to infinity way faster. So large over large, but this goes much larger. So this is going to be x over minus 2. So when x goes to infinity, this is going to go to minus infinity. So we don't know. It's indeterminate. It means the limit really depends on how large this is and how large is that. Even if it's plus or minus infinity, you're absolutely right. It applies. All right?
All right. Thank you.
Make sense? So it's really intuitive. However, if you have something, why we call it indeterminate? So let me go back and want you to fully understand the word indeterminate. Suppose I give you the following limit. Suppose I find the limit as x become close to 0, for example, from the positive of 5 over x. Can you tell me what the limit is immediately? So that goes to 0, 5, and this goes to 0. So this will go to where? Do we know the limit? Do we have any? What's the limit here? Quickly. Quickly, guys. I'm reading.
The limit or the derivative?
Limit.
0.
0. Are you sure?
Oh no, sorry, infinity.
Infinity. Do we have any reluctance in answering the question? What do I mean? What do I mean reluctance? When x becomes very small, so basically you're taking 5 over 10 to the minus 1. 5 over 10 to the minus 2. So this is 5 times 10. 5 times 100. It's not indeterminate because we know what the limit is. I don't have any question in my mind that when x becomes close to 0 from the positive, this is plus infinity. So this is not indeterminate because we know the limit. There is no problem with it. Indeterminate means we don't know it. It depends on the growth of f and the growth of g. So that's really where indeterminate comes into the picture. That's what the word indeterminate means, because we don't know. It really depends on the function. But something like that, we know it. We don't have any issue with it. So that's not an indeterminate form. Okay, so let us go back now to apply L'Hopital's rule, and let's be very careful how to apply it. So first, it applies only and only in those scenarios. And your question made absolutely was correct, plus or minus, absolutely, you're right. So let's take some simple example. Let's find the limit as x become close to pi, for example, of sine x over x minus pi. Okay, it means basically I have to take values close to pi and ask myself, okay, what's happening to this ratio? So first we analyze, always we analyze. Okay, when x become close to pi, sine x become close to what? Let us graph the function sine. Sine is like this. So we have to know the graph of function to be able to analyze those limits. That's a pi, sorry, that's 2 pi, and that's a pi. And that's the sine. So when x become close to pi, the sine x is definitely becoming close to 0. So the numerator equal to 0. The denominator, usually I should start with the denominator. It's really the denominator that starts giving me problem. Now the denominator also, when x become close to pi, the denominator, pi minus pi, equal to 0. So this goes to 0, and this goes to 0. So this is type 0 over 0. L'Hopital's rule is applicable. So we have to make sure we can apply it. Is applicable. And now we apply it. So what does this tell me? And L'Hopital's rule should most of the time get rid of this scenario. So L'Hopital's rule tells me this is equal to, be very careful what it tells me. It's the limit of the derivative of the numerator over the derivative of the denominator. It's not the derivative of the whole thing. It's the derivative of the numerator over the derivative of the denominator. So this will be equal to the limit as x goes to pi of derivative of sine is cosine of x. Derivative of x minus pi is 1 minus 0. And now we don't have really issue anymore. When x become close to pi, cosine x, so let us see, what's cosine x become close to? Okay, let's remember the graph of cosine. That's my cosine. Cosine start here, go down, back up. And this is my pi. So the cosine become close to minus 1. So the limit is equal to minus 1. So the L'Hopital's rule, most of the time, help me to get rid of this scenario and give me a real limit. Okay? Questions? All right, let's do a couple more examples along the same line. So let us say, find, so I have several examples I would like to do. Find the limit as x become close to 0 of arctangent x over x. Okay? All right, so when x goes to 0, what happened? Is it, we have to make, we don't just apply L'Hopital's rule. We always have to check whether it's applicable or not, and that's crucial. When x become close to 0, let us analyze. X become close to 0. So I definitely has an issue. The denominator is becoming very small. What about the numerator? Is it becoming small, yes or not? When x goes to 0, what's the limit of arctangent x? It means, what's the angle whose tangent goes to 0? So arctangent is the angle whose tangent goes to 0. What's the angle whose tangent goes to 0? The angle whose tangent goes to 0 is the 0 angle. So this is because tangent 0 is 0. So this one also will go to 0. So we have to check. So this is type 0 over 0. So L'Hopital's rule is applicable. So this is going to be equal to the limit as x goes to 0 of the derivative of the numerator over the derivative of the denominator. So this will give me the limit of the derivative of the numerator. By now, we know that it's 1 over 1 plus x squared over 1. And this is when x goes to 0. And now analyze it. What happened? This is 1, 1, big deal. When x goes to 0, I will have 1 over 1. That's equal to 1. So it means if I pick up my calculator, basically, which I'm not going to do, and I take x, and then I take this expression, and I start taking values close to 0, and I evaluate. When those becoming close to 0, I'm going to get something close to 1. So really what we're finding, what happened to those when x become close to 0? Okay. All right. So number 3. Suppose I want to compute, find the limit. As, I don't know why I keep giving you 0, there is no reason, of sine x over 1 minus x. Okay, I give you 2 minutes to do it. I want the answer quickly. All of you. Always you analyze. You analyze the expression. Don't do anything. First analyze and then you proceed. Anybody? Shouldn't take that long. Very good. Yeah, let us analyze it. Do we need L'Hopital's rule in this problem? We analyze. When x goes to 0, this goes to 1. So immediately L'Hopital's rule, no, we don't need it. The numerator goes to 0. We don't jump to L'Hopital's rule. That's a very easy limit. 0 over 1 is equal to 0. We have to be very careful not to jump to L'Hopital's rule. We have to make sure we have the two scenarios. All right. Example number 4. I want to find the following limit. Limit as x become close to, well, I don't know why I'm giving you only zeros. I shouldn't, but whatever. Over x squared. Okay, so we're going to find this limit when x goes to 0. All right, again, we'll analyze it. When x goes to 0, what happened? I start with the denominator usually because if the denominator doesn't go to 0, I don't have really a lot of issues. This one goes to 0. Now, what's the numerator? When x become close to 0, what happened to the cosine? So that's my cosine. My cosine start here, go up here. So when x gonna come close to 0, my cosine takes value close to 1. So this become close to 1, means my whole numerator will become close to 0. So this is type 0 over 0. L'Hopital's rule is applicable. Oh, derivative of the numerator over the derivative of the denominator. So this will give me the following. Okay. That's a 0 minus derivative of cosine is minus sine times minus. That's going to give me the sine divided by 2x. Okay. So what happened now? When x goes to 0, we have to compute this limit. Okay, when x goes to 0, this one goes to 0. And when x goes to 0, the sine x, remember sine of 0 is 0. So this goes to 0. So I still have an issue. I applied L'Hopital's rule, and L'Hopital's rule gave me 0 over 0. So what should I do here? I still have an issue. I still have small over small. So what shall I do?
Do it
Don't we
again.
apply it again?
We have to do it again. We can do it as many times as we want till we get rid of this indeterminate idea 0 over 0. So we have to apply it all over again. So L'Hopital's rule again is the limit as x goes to 0 of the derivative of sine over the derivative of 2. So we can apply it 2 times, 3 times, 4 times. We can apply it as many times as we want. So that's the limit of derivative of sine is the cosine. Derivative of 2x is 2. Now we analyze. We're already safe because that's 2. And this one will become close to 1. This is equal to a half. So the limit of this expression, which is actually an expression that comes up a lot, is nothing more equal to a half. Okay. So that's really how we apply L'Hopital's rule. Now, all the scenario I took are 0 over 0, but they don't have to be. We can apply it when we have infinity over infinity. And that's really what we, the example I'm going to talk about right now. And those examples, their importance is not only finding the limit, but studying a little bit how the growth of some functions. Can I move on? All right. So now I'm going to compute the following limit. Find the limit as x goes to infinity, and why not, of e to the x over x. Okay, so first, what happens as x goes to infinity of this? Ex, let's remember the graph of ex. This is ex. So as x goes to infinity, ex goes to infinity. So this is going to go to infinity. And x itself goes to infinity. So this is type infinity over infinity. L'Hopital's rule is absolutely applicable. So L'Hopital's rule tells me what? So this is equal to the limit as x goes to infinity of the derivative of ex over the derivative of x. Means the limit as x goes to infinity of ex over 1. Now when x goes to infinity, this goes to infinity. Okay, so the limit as x goes to infinity of e to the x over x is equal to infinity. All right, now let me ask you one question here. So if when I take this ratio, I get infinity. It means which one goes to infinity faster? It means when x is large, which one is way larger? E to the x or x? If I compute the ratio and I get infinity, it means which one is larger? It means if I take a large x, which one should take larger value? E to the x or x? What do you think?
E to the x.
E to the x. Let us compare those two functions because this is a very important idea. Which function grows faster, e to the x or x? So this limit is equal to infinity. But now let us really. Oh no, you don't need it because here when x goes to infinity, infinity over 1, that's infinity. I'm done. Okay, I'm done. I don't need any more L'Hopital's rule. L'Hopital's rule only infinity over infinity. I don't have this scenario. I have infinity over 1, large over 1 is absolutely infinity. Okay. Now, what I would like to do.
I have a question.
Yes.
For the first part of it, when you check to see if e to the x is infinity and you plug in infinity, how do you get infinity out of that?
Here?
Yes.
That's the graph of e to the x. Okay? That's the graph of the function. Means when x very large, e to a large number. what does it give me? A large or a small number? What type of numbers? So in other words, let me pick this calculator here. If I take E, your battery is low, I've never fixed that. E, and I take it to a large number. What did I get? A large or a
large
small?
number.
What?
A large number.
Large number. If I take E to the power 15, what am I getting?
A large number.
So E, when I raise E to a large number, I get actually a very large number. That's what I mean by e to the x goes to infinity. Are you with me?
Yes.
Okay, the denominator goes to infinity because it's x, it's becoming very large. That's type infinity over infinity. So I have a large over a large number. What happened to the ratio? L'Hopital's rule tells me the ratio is infinity. Okay, but now I want you to understand why ex over x is very large. Okay, now the process for me is for you to understand numerically why this is the case and how I'm going to do it numerically. The way I'm going to do it numerically, because it's a very important idea. Numerically. So L'Hopital's rule gave me the answer. Now I want you to understand it. Numerically means I want to compare x and ex, and eventually the ratio, which is actually, okay, which one is growing faster than the other. So I'm going to take, so as x becomes large, so I want x becomes large, and I don't want it very large because you will see that very minute. So suppose I take x to be equal to 10. Okay, what's e to the 10? Watch carefully. If x is 10, e to the 10 is 22,026. So this is 22,026. So if x is only 10, that's how large e to the x is. So when I'm going to take the ratio, what type of number I'm going to get? A large or a small? Quickly. A large or a small. Look how larger e to the x is than x. This is way, way larger, even when x equal to 10. So this is going to give me 2.6. Now, what if I take x to be 15? Which is much larger? Look what e to the 15 is. E to the 15 is huge. So e to the 15, if I copy my numbers, it's 3, 2, 6, 9, 0, 17. So it's 3,269,017. So when I'm going to take the ratio of 3,269,017 divided by 15, I really don't feel like even doing the math, but I know that this is a large number. I mean, if you do the math, if you do the math, you're going to get, actually, it's 217,934. You're getting a large number. So even if I take 20, e to the 20 is going to be huge compared to x. This is going to be also a large number. Okay, so what's the idea that I'm trying to convey here? The idea is the following, that e to the x goes to infinity, become large, way, way faster than x. In other words, if I take x 15, x is 15, look how large e to the x is. If I take x 20, this is huge. So if I start taking x to be 100, my calculator can barely compute e to the power 100. I mean, I'm going to try it for you. Look, what is it? E to the 100. The calculator gave me times 10 to the power 43. So if I take x to be 100, e to the 100 is 2.6 times 10 to the power 43. So which one is growing faster? Way, way faster. This function run to infinity. Means if x equal 100, this function takes the values 2 times 10 to the power 43. That's how large it is, this function is. So that's why when I'm taking the ratio of e to the x over x, I'm getting something very large, because when x is large, this is way, way, way larger than x. Okay, so this tells me that e to the x is a function that's grow way faster than x. It's a very important idea for us to retain. So e to the x grows extremely fast. Okay. Actually, not only e to the x, very important, grows much faster, way, way faster than x. It goes to infinity very, very quickly. It becomes large very quickly, because these are the values. Even at 15, I am already at 3 millions. At 100, I am at 10 to the 43. So just imagine how large this is really grown. That's why I expected the ratio to be very large. Okay. Actually, it's not only larger than x. E to the x is not only larger than x, actually it's larger than x squared and x cubed. So I will take one more example. So this is a very important idea that we have to retain. We have to understand a little bit how fast functions grow. So I'm going to take one more. Suppose I'm going to take e to the x over not only x, actually I'm going to take x cubed. And the question is, what happened to the ratio? Which one is going to grow faster, e to the x or x to the power 3? So what do I mean by faster? It means when I take x large, which is larger, e to the x or x cubed? That's really what I mean. If I take x to be 100, which one is much bigger, e to the 100 or 100 to the power 3? That's really what we are trying to grab. Okay, so let us do this problem. When x goes to infinity, what happens? E to the x, as now I hope you understood, becomes very large. X cubed becomes very large. So L'Hopital's rule is absolutely applicable, because I have infinity over infinity, and this tells me the limit of the derivative of the numerator, e to the x, over the derivative of the denominator, which is that. Okay, again, what's this limit? This is large, and this is large. Again, I apply L'Hopital's rule. And it's going to give me e to the x over 6x. Very good. Large over large. Again, applicable. And finally, I will get e to the x over 6. Now, when x goes to infinity, 6 is a number. I will have infinity over 6, large over 6. It's still a large number. Again, what does this tell us? Which one grows faster, e to the x or x cubed? This tells me that the ratio is large. It means both of them are large, but the ratio is large. It means the top is growing much faster. So e to the x goes to infinity faster, not only than x, faster than x to the power 3. So here we can say that the e to the x grows faster than actually x to any power, So it goes to infinity very fast. Even if I put x to the power 4, I'm going to have infinity, because I applied the L'Hopital's rule one more time. I get rid of x4, I would get infinity. So x to the x grows faster than x basically to any power. So it's really run to infinity. It becomes large very fast. Okay, so that's the growth of e to the x. And we're not really surprised, because if you guys look at those numbers. If I take x to be 100, x to the power 3 will become, okay, I add 0. So 1, 2, 3, and that. So it's going to give me 10 to the power 9. But look at e to the power 100. It's 10 to the power 43. So this one is growing way faster. Even if I put x cubed, this doesn't really matter. Look how big this is. So e to the x grows very, very fast. Okay. Now, another function that I would also, we need to talk about its growth is the following. So let's take another clean sheet of paper. And I'm going to talk a little bit about the logarithm and analyze the log. So use L'Hopital's rule as a tool to analyze the natural log. So question is, find the limit as x goes to infinity of ln of x over x. Okay, so this is my question. When x goes to infinity, what happened to ln of x? Okay, let's remember the graph of ln. You have to know those graphs to know the limit. ln is when x goes to 0, my ln is here, and it keeps growing and growing and growing and growing. So it never stops growing, okay, but it keeps growing. So when x goes to infinity, the ln of x goes to infinity, okay? So this one goes to infinity, and this goes to infinity. So what happened to the ratio? So this is type infinity over infinity. So it's going to happen to the limit. So the limit is, I can apply L'Hopital's, of course, because infinity over infinity. It's the derivative of the numerator over the derivative of the denominator. And let's now evaluate each one. The derivative numerator is 1. I don't have an issue. The derivative of ln of x is 1 over x. So when x goes to infinity, what happened right there? Let's analyze it. When x goes to infinity, okay, 1 over x become close to what? Back to you. Sorry. When x goes to very large, 1 over x goes to 0. Just if you ever forget, if you ever really forget, ever, they say, okay, 1 over 1,000. Is it a large or a small number? Of course, that's if it's a small number. 1 over 10,000. So if you ever forget, just plug in numbers. I say, okay, when x becomes very large, if I take 1 divided by something very large, what do I get? Something very small. And this is 1. So I will have 0 over 1, which is going to be equal to 0. Okay, so this tells me that the limit. So when x goes to infinity, ln of x over x is equal to 0. So this is a scenario where the numerator is large, the denominator is large. When I compute the ratio, so it's a large over large, I'm getting something small. So do you think which one grows faster? It means when I take large values of x, which is bigger, the ln or x? What do you think? And then we analyze it numerically. That's my question again. If I plug in large values of x, which one is going to take larger values based on this number? ln or x? Which one is really, I'm having what?
X.
Absolutely, x, much larger. Because both are large, large over large. The ratio is 0, it means this has to be larger. The denominator has to be larger. That's how we can get a 0. So x goes to infinity much faster than ln and much slower than e to the x. Now, that's the limit. Now, numerically, because these are growth that we should understand. Numerically, I'm going to compare the values that ln take to the values that x take when x is large. So I'm going to take x here. I'm going to take ln here, and I probably will take the ratio, but you guys will see the numbers. You will understand I don't need the ratio. All right, I'm going to take some large values. I'm going to take a 10. I'm going to take 100 and 1,000. And this actually will show us the picture. I want to watch the ln. So what is ln? Okay, ln of 10, 2.3. So that's 2.3. So that's 2.3 over 10. Okay, so which is, of course, 0.23. So I want to see, to compare. I don't really care much about that as much as I care about you comparing those. When x equal 100, what's the ln? What's ln of 100? 4.6. So I want you to watch. When x is large, look at ln. It's large. I'm not large. It's getting larger. It's very slow. I try to assume that it like goes to infinity like a sloth. Goes to infinity very, very, very slowly, very slowly. So when I'm computing the ratio here, you know, I'm getting 0.046, of course, because this is way larger than ln. I take x to be 1,000. Very good. What's ln of 1,000? It's 6.9. So it's keep increasing. The ln increases very slowly. So I'm dividing them. This is much larger. Even though this is getting larger, very, very slowly, this is way, way larger. I'm getting a very, very small number. Okay, so ln becomes large very, very slow. It means I have to take a huge value here to be able to get a large value of ln. X goes to infinity faster than the ln. So in terms of growth, x goes to infinity way faster or faster than ln of x. So what does faster mean? Because it's a hard word. Faster means, it means if I take a large value of x, x is way, way larger than ln of this value. So if I take x to be 1,000, 1,000 is way larger than ln of 1,000. If I take it to be 1,000,000, the million is way larger than ln of 1,000,000. However, when I compare x to e to the x, we realize the opposite happened. X goes to infinity way, way slower than e to the x. Okay. All right, so we use L'Hopital's rule to understand the growth of those functions because they are absolutely, absolutely crucial to understand the growth of each function. All right, now 0 over 0, infinity over infinity are not the only indeterminate form that we will encounter. There are a lot. I will not talk about all of them. I will talk about some of them. So one more I'm going to talk about today is the following. Indeterminate form actually I have it written. I think I have it right. I don't know. All right. Indeterminate form, indeterminate. Sorry, I have it. All right. Limit of type 0 times infinity. All right, let us read that. What is this? Suppose we have two functions, f and g. When x become close to a, f become very small. And when x become close to a, g become very large, positively or negatively. In this case, we say that the limit of f times g, so that's another kind of indeterminate form besides 0 over 0, infinity over infinity. The limit as x becomes close to a of f times g is indeterminate of type 0 times infinity. Okay, so first, let us understand why this is indeterminate. Why this is indeterminate? Let me analyze what I'm talking about here. Here I have two functions. I'm multiplying them. One of them is approaching 0. Staking is very small. Remember, when I say the limit is 0, it doesn't mean that the function ever takes the value 0. It means the functions take values close to 0, never 0. G is getting very large. So now I'm looking at the product. So now you can think that there is almost like a battle between two functions. This one wants to drag the product to 0. This one wants the product to go to infinity. And the question is, what's going to happen? And what happened is that it depends how small this is and how large this is. So for example, suppose one of them, f is very small. I'm just going to give you a number to try to understand. Suppose f is something like 10 to the power minus 10, very, very tiny. And I multiply it by a large number. So suppose I multiply it by 10 to the power 20, a large number, then when I take the product, I'm getting 10 to the power 10, which is large, because this is way larger than this is small. If I flip the scenario, I take a number which is small. I multiply it by another one which is large. This one is going to be small because this is way smaller. So a small times large, like I had before, could be large, could be small. Actually, it could be anything I want. Now, in terms of function, we can take the following. Suppose I take x squared times 1 over x cubed, and I take the limit as x goes to 0. So I have to take simple example. Now watch the scenario here. This goes to 0. When x goes to 0, this goes to infinity. So one becoming small, one becoming large. What do you think the product will do? I give you a minute. What do you think the product will do? Does it go to 0? Does it go to infinity? 1 minute. You don't need more than that. What do you think the product is going to do? X squared times 1 over x cubed, if you do the math, it's nothing more than 1 over x. Right? Just multiply them. When x goes to 0, and let us assume 0 plus, this is, in this case, is going to go to infinity. So I have something small times something large, and the product went to infinity. And the idea this is going to go to infinity faster than this will go to 0. So if I have 0 over infinity, it's not 0. And it's not infinity. It can be anything in between. And that's called an indeterminate form. Now, how to handle this? L'Hopital's rule now cannot be applied because it's not 0 over 0 or infinity over infinity. So there is a trick that we learn. It's not hard. The trick tells me that we're going to play around with it so that we can apply L'Hopital's rule. So what do I mean by play around with it? So I will show you clearly. To find those limits, it means limit of the form 0 times infinity, we're going to proceed as follows. We're going to rewrite the expression like that. So I take f times g. I'm going to rewrite. I'm not going to change. We're not changing. We're rewriting. We're going to write it such as in the following. F over 1 over g. Now, question number 1. Am I changing the expression if I do that? Yes or no? Because I'm not allowed to change. I'm rewriting. Are those two quantities the same? This and this. Yes, because, I mean, that's the rule of fraction. So I'm not really changing them. Or I can write it. There is no reason why I can keep f in the numerator. Or I can write it g over 1 over f. Regardless of how I write it, I'm not changing. Okay, but what's the benefit of doing this? What's the benefit of doing that? The benefit is the following. My f go to 0. So now, if I rewrite it this way, my numerator now will go to 0. My g go to infinity. By rewriting it this way, 1 over g will go to 0. Are you with me? So by rewriting this way, what I'm going to end up with, what scenario I'm going to end up with? I'm going to end up with the scenario 0 over 0, which will allow me to use L'Hopital's rule. And if I rewrite it this way, I will end up with infinity over infinity, which will allow me to use L'Hopital's rule. So let me sum up, and then we'll do an example. If I have 0 times infinity, that's indeterminate because the 0 wants to drag the product to 0. The infinity wants to make it very large. So it depends who wins the battle between them. So that's really intuitive what's going on here. So in this scenario, I have to rewrite it so I can reproduce the scenario 0 over 0, infinity over infinity, and then use L'Hopital's rule. So a very quick example in the last 2 minutes I have. Now, which function to pay, which way to write it, it's really a matter of judgment. We see which one is easier to work with. So let me do that. An example. Find limit. Sorry. Find limit. As x become close to 0 from the positive of x multiplied by ln of x. It's not divided anymore, but multiplied. So always analyze, always analyze. Now, what happened when x become close to 0? Remember, and that's crucial, x is never 0. When we say x goes to 0, means x takes value very close, 0.01, 0.00. It's never 0. So you never plug in 0 in here. It's something very close to 0. So when x becomes close to 0, this is not 0. It takes value close to 0. Close to 0. It's important. What about ln? Now, I just drew the graph of ln because I want it to be kind of drilled in your head. ln is like that. That's the ln of x. This is a 1 in here. Okay. Now, I had to take x from the positive because ln is only defined when x is positive. So if I remove this, the problem doesn't make sense anymore. Because if I don't put positive, I'm going to allow x to take negative values. And this will make no sense. That's why I'm forced to put positive. Now, when x becomes close to 0 from the positive side, so here we have to know, when x becomes close to 0 from the positive, ln, it means is minus infinity. Means if I take my calculator and I plug in very, very small values of x, my ln start taking larger and larger negative value. It's very important to know those facts. So when x goes to, this becomes large, negatively large, but it's still large. So this goes to minus infinity. So this tells me we have a type 0 times minus infinity. That's absolutely indeterminate. So now the question is, we now rewrite it. Means one of those functions, I have to bring it down to the denominator. So we're going to rewrite. At this stage, I'm not using L'Hopital's rule. I am just manipulating algebraically so that I can use L'Hopital's rule. So this will become the following. The limit of. So now the question is, which one to bring down? So we have to rewrite it, as I said, f over 1 over g or g over 1 over f. One of them has to be somehow brought down. The question is which one? And I don't have a rule. I have just, which one is easier to bring down? Is it ln or x? So in this case, I'm going to rewrite it as ln of x over 1 over x. Okay, now I'm not using L'Hopital's. Be very careful. The only thing I'm doing now is I'm going to rewrite it. So I haven't changed anything from here to here. Nothing. I'm just rewriting it. I chose to bring 1 over x because it's easier than bringing 1 over ln of x. Now, the magic. When x goes to 0, it's still going to go to infinity. When x goes to 0, 1 over x, this whole thing, is going to go to infinity. And now I have infinity over infinity, actually minus, but as your classmate at the beginning of the lecture said, can I use it? And the answer is absolutely no. Now, L'Hopital's rule is applicable, absolutely applicable. And let us see how we're using it. It's the derivative of the numerator over the derivative of the denominator. I know that I'm out of time. I need 2 minutes to finish this problem. It's the derivative of the numerator over the derivative. Now, let us compute each one of them. ln of x is 1 over x. The derivative of 1 over x I will a little bit wave my hand, but I think you should know it, is minus 1 over x squared. Okay, so let me write here, the derivative of 1 over x is the derivative of x to the minus 1. It means minus x to the minus 2. Just to remind you, it means minus 1 over x squared. All right, so now this limit. Now, it will be stupid from our part to not simplify this limit. I mean, I have 1 over x, I have minus 1 over x squared. We are going a little bit to simplify. Otherwise, it will not be smart to just apply rules. So I'm going to simplify this by using the property of fraction. So that's 1 over x times minus x squared over 1. So now this is algebra. It's not anything. It's just I'm doing algebra at this stage. So finally, that's the limit of minus x squared over that minus x as x goes to 0 from to positive, which is equal to 0, and of the problem. Okay, so an algebraic manipulation is in order so that I can create a situation where L'Hopital's rule can be defined. Okay, and of the problem. All right, so for tomorrow, your online homework is already there. Please get started, and as usual, any questions you have, you're welcome to ask tomorrow. And remember, your exam is this Friday. Please ask me questions every day about anything you want. Okay, good luck, and see you tomorrow. Bye, guys.
Have a good one.
What?
Have a good day.
Thank you very much. Bye-bye, guys.